Oh, it's 7:59.
Okay, everybody, usual rules, laptop shut, pay attention. Uh, those of you who are not here, you're probably not hearing this. Lady at the back, can you shut your laptop? Yes, please. We will be posting the attendance for the past several classes on Canvas either today or tomorrow. It will count. And so just letting you know. Also, it's a tradition in the course to actually have one or two lectures, 1 or 2 or 3 lectures actually be held by our TAs. And so I picked the most difficult topics because that's what these lectures are. And I think they work hard, they actually practice, we're doing our best.
Hello.
And it is my experience that they usually do a better job than me when it comes to covering the topics I give them because they're more afraid of you than I. So today it's Shikhar and Josh's turn. They're going to be talking about transformers and large language models. After the class is done, please give them a hand, guys. Right.
Cool. So, good morning, everyone. And today, me and Josh will present the lecture on transformers and LLMs. So, yeah, I guess we'll start then. So, anyone like who's been doing deep learning and looked around stuff, they must have seen this gigantic figure of transformers. And as complex as it looks like, it does have like a lot of terminologies around it, which even today I am confused about some of them, and I'm sure like a lot of people are. So during this lecture, we'll try to like make these concepts more clear, more understandable, and hope that we are like a little more knowledgeable than we are just now. Okay, so yeah, it's like difficult to understand all of these. Yeah, let's go back to our previous lecture where we had this simple example of inputs and outputs, a simple task of machine translation where we have like I ate an apple and the German translation of Ich habe einen Apfel, whatever it is. So now we try to do this via transformers. The transformer obviously can't take just the literal terms as input, so we need to start with like processing the inputs, as you can see on the right, on the bottom left of the transformer of the architecture. And we start with the processing of inputs by generating our input embeddings. We pass the string to our tokenizer, we get the tokens, we pass it via an embedding layer, and we get our embeddings. These embedding layers can be anything that you want, like word to egg, glove, or you can also have your own embedding layers. And at this point, we define like a dimensionality of the embeddings, which will continue like over the rest of the like lecture as well, which here in this case is 5, and we write it as D model. So yeah, we look at this diagram, we have our inputs, we generate the input embeddings. And at this point, every token knows about itself. It knows like what it contains, and it knows like what it has to do. So now that it knows about itself, but it also needs to know about things around it. It needs to know like 8 needs to know what is I needs to know like what is and. So everyone needs to know about the people around them, the terms around them. And at this point, they just have their individual context, but we want to add more context into it, like from the rest of the tokens that we have. So we wish to have some black box of sorts where we like send in our input embeddings. They learn from each other and they learn from themselves too. And once they learn to add context from everyone, we get an output which is contextually rich. Now, at this point, every embedding would know more about the people around them and the things around them and around themselves as well. So the thing here arises, how much should A learn from B, right? What should be the weight that A gives to B and B gives to C and B gives to itself as well? So we need to find some kind of a weight of sorts where we get to know that how much does token I learn from token J. And this weight we'll call as alpha I of J. Again, once we have all these weights, we have all the terms, do we sum them? Do we take a product? That now we'll go and explore like what exactly happens in this black box of sorts. So from lecture 18, in our bid to find the attention weights, we go back to attention that we studied. We had the formula of QKV, which takes a softmax over the Einstein product and calculates like the final values. But what are these query keys and values? Like usually, even before this lecture, while I was preparing it, I was not completely sure about it. I had to like go and study a lot around what exactly query is, what key is, what values are. So I hope you guys are also inquisitive about it. So we first like try to draw a parallelism. I guess like since most of us are computer science students or like have done some programming of sorts, we have seen like such key value structures as a database of sorts where you have a key value store and you want to find information out of it. You want to know like what it contains. So what do you do about it? You form a query. You have like a query which says that, okay, give me order details of order 104 or order 106. So once you say that, you have your query, you have your key value store, you use your query values and search along the keys of the key value store, right? You find, okay, which one is order 104, which one is 106. Once you find them, you like highlight them, and then you pick its values. So this is like a three-step process. You look into the complete database, you identify the right things, and then you like take out the values from them. And the order, like the order of like execution, like 104, the information for 104 does not depend on the information of 106. They can be done at the same time. You can find 104 and 106 all at the same time. So let's like try to distinguish these three terms then. The queries are the ones that search for information. The keys are the ones that actually interact with this information. And the queries and keys interact with each other and try to find what kind of like it tries to distinguish like object A from object B and tries to identify which object is most relevant. Once it does that, it tries to find the actual details of the object. Now, one distinctness between this and our attention mechanism is that this is more of an exact match. We don't do an exact match in attention. We try to find weights, like how much priority you want to give to like context A, context B, context C. There is like no just, there's not just like a single picking of any context. So that is a distinction where here we do a more soft match of sorts. So yeah, we have our query, we get our key value store, we find the keys, and then we pick that exact value. You have another query, you go back to your key value store, you find your keys, you have your values. Now comes the parallelism, and yeah, it can come at the same time. And now comes your actual parallelism with your attention concept. So you have your queue, you multiply it by QKT, you get your, you try to like search the queries on the keys. Once you identify the correct keys, you highlight them by doing a softmax. And once you get your final attention weights, you pick out the values for those keys. And again, this is an exact match. An exact match does not happen in this case. It will pick something from everything. So this key this step that we see, softmax QKT, is also called an attention filter of sorts, which you'll like keep hearing around that, this is the actual attention filter, which tells you that how to filter out like actual information from a bunch of objects. So now that we know what a key value store is and we know like what actually happens in the attention mechanism, we can do a single simulation of how the attention works. So in this example, we'll just go for object like for the key I1. And first step, we take out the projections of these keys. The reason we take these projections is that we don't really want to overly rely on our input embeddings. We want the model to like learn more from these embeddings and extract more information out of it. So we don't use these embeddings directly, but we take a projection out of it. Once we have the projections, we take the Einstein product for like query 1. We'll start to look at object key 1. Once it identifies, it calculates its weight, takes the softmax, and we have our value multiplication, and it knows that how much value it needs to extract from this particular object. The same thing happens with query 2, with query 1 going to key 2, query 1 going to key 3, going to key 4, going to key 5. So every query will look, so like a single query will look at all keys. And once it looks at all keys, it does so the softmax that I did at step 1 does not happen right there. It first like gets all this, and then once it has all the products, it does a softmax and gets the actual attention weights that we've been searching for. Once it has the attention weights, it multiplies the values to it, and a sum is taken, and you have your finally contextually rich embedding, the black box we were searching for. So this is your final representation of the contextually rich output of your I1 and all the weights related to just I1. I showed this in a sequential form just to make it more understandable, but all of this happens at the same time. So that's the like main power of transformers, that you don't have to like do sequence to sequence, but you can just do the entire sequence at once. Yeah, it can be parallelized. So yeah, there's a poll question for you now. Yeah. I think time is up. Anyone wants to answer? I'll not point at you. What? The poll is not visible. Okay. Yeah, anyone wants to answer? Yeah, pretty good. So yeah, to calculate the attention weights for I2, you'll use just the query I2 or query Q2, but you'll use all the keys that are available. And you scale the QKT. I think I missed this in the lecture just back, but yeah, the term that you see here is done, the division of the softmax, like the QKT product by root D. Like there's no particular explanation for it, but a general consensus of sorts is that it is done to provide numerical stability because you're summing a lot of inputs and you don't want them to like explode. So yeah, now that we've made the embeddings more contextually rich, and we know that the transformer does processing in more of a parallel fashion, how does the transformer know about the positions of the objects? So if you have this sentence, I ate an apple, and end of sequence, it is starkly different from apple ate an I. But when you process them parallelly, the transformer will calculate the exact same weights for both of these objects if it does not have like any positional information. So that's where we have our positional encoding stepping in. And we need to tell the transformer like what the exact sequence of the terms was. So now that you look at these positional encodings, like what are the minimum requirements that you have for them? First of all, like as we saw from our seek-to-seek model, there should be like some representation of time, which tells that, okay, A came first and then B came. Second of all, it should not be cyclic in nature. Like it should not be that after a certain point, A behaves exactly as like say Z or something. So it should not be cyclic. It should have some representation of time. So some very simple and straightforward implementations from here look like, you can just have a pt plus 1, which says that p of t plus a constant factor, or you can use some exponentials of sorts as well. And this like seems very simple and easy to implement and should work for our use case. But there's a problem with that, and can anyone identify what is the problem here? Yeah, correct. So these values, even though they are like very simple and easy to implement, beyond a point, even for like very small values like 10, they start to explode. So this will make our model unstable, and we do not want to like do anything of that sorts. What is the next thing we can do? We need something that is bounded in nature, right? So another candidate that we can have is something like pt plus t dash, which is equal to like you have a matrix M, and you say that you can obtain a new positional encoding from an existing encoding by just having the difference between them. And this basically is, here M is your rotational matrix. This concept is a little tricky for me at least. And when you look at M, there are like some minimal requirements that M should also have. First of all, M should be unitary in nature. We do not want to like explode over multiple products. Say like, because every time you're taking a product and you don't want to like explode over time, that will like again bring us back to the bounded problem. And the other thing should be that the magnitudes of eigenvalues should again like be 1, because we don't want it to like either explode or like vanish over time. So these two are some of the minimal requirements that we have for our M matrix that we have here. And the good thing about it is like the way it is implemented, you can actually learn this matrix as part of the transformer like process. This matrix can eventually make its way directly into the Einstein product, and you can like learn it there. So it'll always produce your unique embeddings at each time, and it can also be trained. Now, this concept looks a bit non-trivial, so I've cited the exact paper that you can refer to, which is like the rotary positional embeddings, and you can see, like people who are like familiar with complex numbers and math can actually see that the matrix that we see for a very simple two-dimensional the M can actually come out of the product. You can represent it in its Euler form, and once you have that, you can just keep on taking products and have like your magnitude stays the same, and every time you take a product, you get something unique out of it. And yeah, there was definitely we had improvements over multiple tasks based like instead of like using the simple positional encodings that we had. So this is, yeah, you can refer to this paper if you have like more details and doubts. So let's look at what is actually used in here. We use the sine and cosine trigonometric functions in place of our positional encoding, which solves our problem of being bounded. But like we know by nature, trigonometric functions are cyclic in nature, right? So we need to still put some constraints over g of t so that it does not form a cycle of sorts. How do we do that? So yeah, so g of t, first of all, it should have like the same dimensions as the input embeddings, because if you look here, you have like the input embeddings which are being added to the positional encodings. So they must have like the same dimensions. That is one requirement. And the other requirement is that they should produce overall unique outputs in total. So the authors make use of like this particular, you can still call it a hyperparameter, like the actual function that is inside of it. When you look at like 10k to the power 2 of I by d model, across for a like these are like both these formulas are used for like the single position. So for a given position across dimensions, you see that the value of 10k that to the power 2 by 2i by d model will produce an irrational number of sorts. When you multiply this irrational number with any rational number, it still continues to be irrational. This total product will always be unique, so it will never cycle in nature. Like another explanation that I can give is that if you fix your dimension of a particular embedding, suppose these are your input embeddings, and you fix a particular dimension, then your product, then your bottom, like the denominator stays constant, and you keep multiplying values to it. So for every dimension, you'll always get like a unique number out of it, and it will like it is expected never to like cycle in sorts. So that is the like this is again just a hyperparameter, and this is like what the authors made use of. So we simulated like a few values for our like 5-input, 5-dimensional model, and we can still see that some dimensions might have like similar values, like dimension 4 has similar values for 0 and 1. But on an overall sense, every position is unique. Every position has like a unique final embedding out of it. And that solves our three requirements. It is not cyclic, it is bounded in nature, and it has like a representation of time. As you can see, it moves along the dimensions. So any questions at this point? Yeah.
So if we are using a fixed denominator, does that automatically mean that we are setting some sort of bounded limit for the number of dimensions we can have for the transformer?
It is.
Like exponentially large, but still.
Yeah, like you can say that, but when you take a product and you put it across like the trigonometric functions, you will always get something unique out of it.
Regardless of the number of dimensions?
Yeah. Like that is expected to happen.
Yeah. My question is more like, does it kind of diminish over time the magnitude of positional embedding, or kind of enforce that?
So that's why I had this like visualization of sorts. So this is over like 10 positions. You see like it never really diminishes, and it like uses like values from across its spectrum.
So if you actually go back a few slides, before keep going back. Yes, okay. So as you can see, if M is a rotational matrix, then the length will never change. It cannot diminish.
Yep. Thank you, Prof. And any more questions that you have at this point? Otherwise, we'll go further. Okay, so at this point, we have had like two kinds of context to the initial like dormant input embeddings that we had. We have are positional encodings that we add before feeding the encoder to the encoder as input. And we studied that we had the attention-related weights and values that we have to the input embeddings. So now that we know these two things, we have solved our black box of sorts, and we know like what exactly happens inside it. And now let's like dive deeper into the encoder that we have on the right here. Okay, so the encoder you see there, it has like written like multi-head attention, and over time you'll see, you must have heard of terms like self-attention, multi-head attention, encoder, decoder attention, and like 10 different types of attention. So let's start with like self-attention for the beginning. So this is a very famous example that we have. You must have like probably read it online or somewhere, that you have a sentence, the animal didn't cross the street because it was too wide. Now we as humans can easily tell what it means because we have like a lot more knowledge than the transformer. But how does it know that whether it means a street or it means the animal? So the transformer needs to perform some kind of coreference resolution of sorts. Every word needs to know what it is representing and what the things around it is representing. So we start with every word starts to look at themselves. The will look at all itself and all the words around it. Animal would look at itself and all the words around it. Accordingly, it will look at itself and all the words around it. And that is the self nature of this attention, that the entire attention that is calculated inside the encoder block itself. Like the attention value is like all the values and things that are used from the block itself. So every word is looking at itself. So they are trying to like find what every other word means. So that is the self kind of nature that we have. And the query inputs here are equal to the key inputs are equal to the value inputs. That's like an implementation detail that you can always keep in mind, that in self-attention, you have all the inputs for QKV equal. And once you have these self-attention inputs available to you, we can now again proceed with our normal attention calculations. So from this point of the lecture, try to focus more on the different dimensions that I'm mentioning. These dimensions are like, in our homework systems, we just like put a debugger and find what dimensions match and just make the code work. But these dimensions have like a higher meaning, and they have like reasons why they are something. So we start with our input embeddings, which are of dimension, the D model that we defined initially. We have it as, for each of the terms, we have like D embeddings. And we have our query, key, and projection weight matrices, which are of D model, and again D model, because every dimension tries to learn something like about each dimensions. So we have, these are our dimensions of these matrices. For self-attention, we take the same input for all three weights. We calculate our Q projections, key projections, and value projections. And the dimensionality of the actual input does not change. It is T times T model, and here also it's T times T model, but it is like a lot more rich. Once you have these, you calculate your simple QKT product. And again, take a look at the dimensions. The actual output of this QKT is T cross T. What does this signify at this point? So this basically is your attention filter that we just saw previously. And T cross T means that every term now knows which term to focus on and by how much. So that is the actual attention filter that we calculate, and it has dimensions like T cross T that we have here. Once you have them, and there's like the complexity, and that's also like a very like well-asked question in interviews. Like they'll ask you the dimensions, they'll ask you the complexities and stuff. So we are building a T cross T matrix, and every matrix has like D multiplication. So like final complexity comes out to be like theta of T squared D model. So once we have that, we multiply our value projections, and we get our final attention value. This is your final self-attention for just inside your the encoder model. So at this point, the model now with this attention, it knows that it can do the coreference resolution. It knows how much attention that it needs to pay to animal and it needs to pay to street. But these textual things, these literature does not just have one single concept to learn from, right? It needs to learn a lot more about things. Coreference resolution, suppose it is solved in this particular case, but we still need to look at sentence boundaries, semantic relationships, other things like parts of speech, and more. How does the model know more about it? Here comes the actual idea of the multi-head attention that we have here. So we have our self-attention where our input embeddings are T times T model and our weight matrices are D model times T model. We split these weight matrices into H heads. So all the matrices that you see, we split them into H different heads, and the dimensionality of this matrix changes to like D models times TH. And if you see here, even though we have like more matrices, the number of models to train, the number of parameters to train still remain the same. So bringing it into a multi-head form does not change your number of parameters as such, at least in this implementation. So now that you have like individual weight Q query and values, you again like go ahead, you calculate your individual projections and keep your focus on the dimensions as well. Once you have your individual dimensions, you calculate for all of these QKI pairs. For all of the heads, you calculate your new attention values. And eventually, when you have like each attention value that you get, you merge them together. And your final, like you concatenate them together. And your final multi-head attention, again, it comes back to T times T model, which was the case in your single head, like your single head attention as well. So in this particular implementation, you maintain like your attention weights and your, sorry, the attention parameters across like implementations. Any questions at this point? Yeah.
So we are remaining the number of parameters.
Yeah.
Regardless of multi-head and.
Yeah, in this implementation, we are doing that.
Why does the multi-head attention can learn different?
So if you look at the different projection matrices that we have, each matrix like gets trained like for its own set of parameters. So earlier, like you're training the entire matrix like at once, but now you can train them individually, and each of them can learn something different.
So we hope if this.
Yeah. Yeah. Any other questions?
Could you repeat that one more time? Like, why does the number of parameters not change?
So if you go back to the single head attention and you look at the dimensions that we have, it is D model times T model, and this is just like a single head. So your input embeddings have the dimensions of T times T model, and your out, like the weight projections also have those outputs. When you go into multi-head attention, you simply divide your D model by the number of heads you have. So your matrix, which was this big, is just now pieces of this, like this much length. So the number of parameters are still the same, and you can like tune them differently. So that's why, yeah. Anything else?
Why don't we take a sum or a mean of all the heads?
So one reason for that is you want them to like learn differently, and the like yeah, there can be one fault with that they are all being trained separate. So how do they learn from each other? For that like we'll come we'll talk about it later. But the current implementation assumes that you just like concatenate them instead of learning.
But it doesn't each head work on different parts of the input?
No. If you see the product that is happening here, it's T times T model, and your product is again D models times TH. So the actual multiplications are still happening across like all the dimensions. And then you get your output as T of H. Any other question? Okay. So yeah, so you concatenate them. You have your final attention value. The model is now assumed to learn, a lot more things. And it is like there is no proven thing that every head learns a different thing, but it is just a convention that now that we have the outputs and we have like the actual results, we can form a theory around it. So that is like the current theory that every head learns a different part of the structure that we have or the sentence. Okay, so once you've solved your multi-head attention, you move a step ahead. You see that there's an add-norm layer. The normalization layer is simply to stabilize your attention weight so that you have like a mean of 0 and standard deviation of 1. And as we've like studied earlier, stabilization helps you get faster convergence and removes any irregularities and exploding of gradients or vanishing of gradients of sorts. So that is what the normalization does here. And the residual inputs, as again we have studied in previous lectures, help you to like train deeper and deeper models without like having any loss of knowledge across layers.
Is that a batch normalization or a vector norm?
Yeah, like basically. So yeah.
Is it answer the question?
Oh.
Is it a batch normalization or a vector norm?
Yeah. Is it like a batch norm or a vector norm, you guys? Anyone wants to answer? Yeah, it's a vector norm. Yeah. So we normalize it across features and not across like the inputs. So yeah, we have our normalization step, we have the residual addition steps, and once we are through that, we now that we come to that point that we have all the heads have been concatenated separately, how do they learn from each other? So one reason we have the feed forward layer is that at this point, every head can contribute its knowledge, and the model can now learn like more about each other, and it helps like there can be like some complex relationships and stuff, and it can like now learn basically from all the heads together and produce a better output from here. And again, like once you do that, add a norm is done again to provide like a similar benefit that we saw just earlier. And at this point, we finish our encoder flow. You can chain a lot of these encoders as much as your compute supports or whatever. It's still a hyperparameter, and the output from encoder I will go as the input to your encoder I plus 1. So we are through to the encoder at this point. Any questions? Yeah.
So the final output of the encoder is the size of the input length
Yeah.
and the time against the hidden dimension that we choose.
Yeah.
That doesn't.
Yeah. Any other questions? At this point of the lecture, we have already finished like a lot of the things we were not clear about. And if everyone is good, then we can proceed to the decoder now. Yeah.
I just have a quick question. So you mentioned normalization. Why do we do it across the vector and not across the batch, where in PNNs you do it?
I think it's more because you want to like you don't want to like destabilize your you don't want to like give more preference to any feature, or you don't want to like make it like you want to like give each of the inputs like equal weightage, so you would not like do it across the inputs, but you'll rather do it like across the features so that it does not like like explode or something.
So you care more that each embedding is kind of centered at zero and has a.
You can't really do this as a over the batch. If I have a batch with different lengths of inputs, they're all going to be different lengths.
Yeah, that too. Okay, so should we jump into the decoder now? Okay, cool. So now that we go back to our task of machine translation, we had our inputs, we had some targets. We wanted to like do the translation here. We have done our part towards processing and like representing the inputs. And now we move to the targets. So again, very similar to how the inputs look like, you have the very first step is again like producing and embedding and adding some positional encoding to these targets that you have. So you tokenize your targets, you pass them through the embedding layer, add the positional encoding, and you have a good representation of your input, of your output targets that you have. Once you've generated your target embeddings, you step into the decoder, and you see this masked multi-head attention of sorts. Now, this is something, again, new that has come up across this lecture. So let's try to think what this masked multi-head attention is. In a general scenario, how does a decoder work? Like when you use ChatGPT or when you use any other seek-to-seek models, how do they work? Like they work sequentially, right? They work like in the training time when you're using teacher forcing, they work in an autoregressive sense where you generate something, you put it back, generate, put it back, generate, put it back. So if we try to perform the same thing at the time when you're like doing your training, this would mean that you have to like go through each of the 7 steps sequentially. You prompt the model with the SOS. It sends you the next output. You prompt it, you put it back, next output, back, output. So you'll have to perform like T separate iterations. Can all of this be parallelized? Let's see. At the time of training, when you're using like teacher forcing as well, you have access to all your target outputs, right? So you can maybe make better use of them. You need to produce like T iterations, and you have like T outputs as well. So can you like in some way try to make use of the outputs itself? What should be like the minimum requirement if you're trying to like use the entire output parallelly? The outputs, yeah. Oh yeah, sorry. So the outputs at time t should only pay attention to the outputs at time t minus 1, right? Because you don't want it to see the future. It should only have the context of what it has already produced and not like what it is about to like produce. How can we do that? We have t outputs. We have like t terms that we need to produce. We have all of them available at the same time. Can we mask them so that the model at time 1 will only see SOS? The model at time 2 only sees like SOS and Aish, and so on. So the model at time t5 would only see outputs until t5 and not beyond that. So that is the kind of mask that we talk about here. And how do we implement that? You can simply replace these mask filter values, that the attention filter values that you generate by minus infinity. But like, how does that help? Anyone? Why only minus infinity? Why nothing else?
Once you put it through softmax, it becomes 0.
Yeah, that is correct. So once you do a softmax over your QKT calculated values, all the minus infinity goes down to 0. So the model, so like the sequence in itself cannot pay attention to like those weights because those weights are already 0. So that is the concept of masked multi-attention that we use only at the time of decoding. We have our QKT product, which is like terms, we have the attention filter there, we add the mask to it, and we have our mask attention ready. This is and again, this can be done across like multi-heads, so it will be like the masked multi-head attention of sorts. You calculate your values and you perform, like if you look at the diagram, once you pass the like masked multi-head attention stage, you do the add norm, which again provides similar benefits, and we come to our like final concept that we will study about this, which is the encoder-decoder attention, the multi-head attention that you see in the second step on the decoder. So at this point, any questions about the masks? Yeah.
At the point page 98, yeah, here, the black value at the attention mask is minus.
Yeah, yeah.
Then we.
Yeah, you overwrite whatever values you calculate with that, and you do a softmax, and everything vanishes from there. Yeah. Any other questions? Okay. So now we'll step into what the encoder-decoder attention is. So until now, we've studied like encoder self-attention, decoder masked self-attention, and what were the input values that what were the values we made use of there. So in the encoder self-attention, the entire attention was contained inside the encoder. You had the queries, keys, and values, all of them came from the encoder inputs. For the decoder masked self-attention, you had the queries, keys, and values that again came from inside the decoder itself. But if you see in the diagram, the final output from the encoder comes back to the input in the multi-head attention for the decoder. Why does this happen? Let's have a look. If we go back to our previous attention discussion or the parallelism that we draw, we had some queries that were looking for information, and we had like a queue or a key value store that had the information. So at this point of decoding, the queries are the ones that are formed inside the decoder, because the decoder is the one that is looking for information. The decoder wants to know, like, what do I produce next? And the keys and values come from the final output, like the final generated attention output across all the encoders that you have. That has all the keys and values, all the information that the decoder is looking for. So similarly, we have the queries for the encoder-decoder attention that comes out from the decoder inputs, from the whatever goes inside the decoder. And the encoder provides the keys and values, the final encoder outputs. And just a small note, it's not like parallel in nature, like that encoder one will give the output to like decoder one. All the final encoder output goes as input to every decoder block here. So now every decoder has context from what it needs to do, and it can like basically go about doing its task of decoding. And again, like just a little attention to the dimensions. We have like the initial query from the decoder and the key from the encoder. The TD there is the terms in the decoder, and TE is the terms in the encoder. You move ahead a step, you do the softmax, you do the value multiplication, and you have your final attention, which is T times of the decoder terms and D model, the dimensionality that we fixed in the very beginning. So any questions about the encoder-decoder attention? Yeah. Yeah.
The first key tokens for decoder when with only starting token.
So when you send in the start token, it'll generate like a representation of it. It'll go and prompt the encoder output that it has. That will provide it the actual values and it'll like go across layers, do the linear and softmax, which is not available, and predict the output. But since we are doing a teacher forcing method, we are ignoring that output and we'll use the target that we have at time of training. Yeah, like when the decoder does not have any weights as such, so we use the outputs that we have already as the next output. Okay. Any other questions? Yeah.
So the key and the value are taken as like sliced from the encoder output? As in like do we
So no, like the entire value that comes out goes into each of the decoder blocks. Why? Like there's no slicing of sorts.
So like the dimensionality of the query, the key and the value are the dimensional earning model. Okay.
Yeah. So you have your query dimensions, which are t times d, and the key dimensions, which are te times t. When you perform the product, like doing a transpose, you get the output of td times te. So that attention filter is how much does each term of the decoder needs to pay attention to each term of the encoder. And then you're like, once you have that dimension, you multiply it with the values that you have, and eventually you get rid of the encoder dimension once you have your final output and the attention there.
And you do multiple SOs as well?
Yeah, you can do that. Like it's a multi-headed engine there. So that solves the problem of your decoding. And again, you do some form of normalization and add the residuals to get like a more stabilization effect. You do a feed forward to learn more about everything. And once you have that, you have your final decoder model ready. And again, you can chain them all, and you like to like the NX that you see, that's like n times decoder. So you can chain them all and add as many as you want. And yeah, you get your final decoder output, which is of the dimension RTD times T model. And you take a cross product with the final vocabulary that you have, which is V times T model. So basically, once you have your final decoder outputs, you project it over the entire vocabulary space that you have, and you take a softmax to like get the best term out of it, and that is where you get your final logs, the output probabilities that you can use to find the next term that is generated. Yeah. Any questions? So yeah, you have your all of the terms, and you have across vocabularies, and that will bring us to the next poll. Okay. Yeah. That's fine. 10 more seconds we have. Oh yeah, I can maybe take 10 more. Okay, anyone wants to answer? No? Anyone on Zoom wants to answer? Okay, well, B and E were your correct answers, so kudos if you understood that. Yeah, at this point, we have completed our entire task of machine translation through the entire transformer, and now Josh will take over from here to talk about the rest of the lecture and large language models. Oh, yeah.
All right, haven't used this before. I hope that people can hear me. Okay. So, all right. So we got to this part of the course where we get to talk about large language models specifically, and it hasn't been historically part of the course or a dedicated part of the lecture to a discussion in LLMs in specific, but we feel that it's important to at least include that part of discussion. At this point in time in this semester, because generally with any technology, when it comes out, there's going to be a big hype where people say, this is absolutely fantastic, this is great. But then after some time, it sort of just distills, and people sort of get disappointed a little bit about how it's actually not that magical. But then after some time, it picks up again gradually, and now it becomes the establishment, right? So my personal feeling is that LLM is definitely in the hype stage right now, which is why it has gotten a lot of attention. So it's definitely important for us to understand how LLMs are made. And since this lecture is about the transformers, it's relevant because LLMs are made from transformers, right? That's that's the centerpiece of whatever LLM you can find today. So let's dive into it. This is the familiar diagram we've been working on for a while for now. I'm sure you're familiar with it. And notably, I want to point out that there are mainly two parts to the transformer architecture, right? There's an encoder, which is responsible for representation, and a decoder, which is responsible for generation, right? And by representation, I just mean that the model takes in some text and output a hidden representation, which is not recognizable to humans as text, but is meaningful to the machine, right? And generation just means the model takes in whatever it wants, basically hidden states and maybe output text, and outputs tokens that are legible to you, right? That's what I mean by generation. So if you look at certain LLM documentations or even discussions out there, you're going to find things like something is a encoder-only LLM, or something is a decoder-only LLM, right? And I bet you're going to be wondering, wait, what's happening? Because is that just half a model? Like, isn't just an incomplete model? How can an encoder be itself an LLM, right? I had that question when I first entered the discussion, so I feel it is important to explain that. So here it is. Let's first look at what the encoder and the decoder are respectively responsible for, right? So if you look at this, the encoder is responsible for taking input tokens, which basically means raw text, and it outputs hidden states, right? And the decoder takes in output tokens and encoder hidden states, right? The output tokens, it takes in here, and the encoder hidden states, it takes in via cross-attention, right? And it outputs tokens. And notice that for the encoder, I put in that its input is called output tokens, and that is because the output tokens are precisely the tokens that it outputs in its output channel, right? When it outputs something, that token will go back to its input. That's called autoregressivity, right? So this is the sort of interface with the encoder and the decoder. And when you look at how the internal mechanism in attention works, encoder models can see all the time steps in the model. Basically means that for it to form a hidden representation of a certain token, it can take information from its neighboring tokens in both directions. We've just talked about that, right? For a decoder to form a hidden state about a certain token, it can only take information from things before, sorry. And it does that by masking things it doesn't want to see with negative infinity. We just talked about the reason why, right? The encoder does not output tokens, so there's no discussion of autoregressivity, and the decoder is autoregressive because it takes in as input its previous time steps outputs, right? We talked about that. So if we think about it, that is basically the recipe for an entire LM that lies within each of these components. Because think about it, we can make the encoder output tokens too. And we can do that by appending a module that maps whatever hidden state dimension it is to the token dimensionality, to the token space, right? If we do that, then we sort of have an LM in itself in that it is capable of reading text and outputting text, right? The same can be done via a decoder because, think about it, we say the encoder is responsible for generating hidden states. You want hidden states from decoder? Sure, here it is. You look at the, actually, let me get this. The encoder outputs text with this linear and softmax over here. If you just do not look at that, you look at one layer before this, then there it is. That's your hidden state, right? So with decoder, there is definitely a hidden state. With encoder, there's definitely an ability to output tokens if we make it to. So definitely, an encoder can be made a seek-to-seek LM. Encoder can read and write tokens, and decoder can be made to output hidden states. So really, when you do either of these things, you have an LM by itself, right? So an encoder-only LM is not any less powerful than an entire LM. It does not explicitly use a separate decoder for outputting, but it definitely can output. A decoder-only LM is not any less powerful than a whole transformer. It does not use an explicit encoder for hidden state. It just uses its own reading in for that. So that is what we mean by an encoder-only LLM and a decoder-only LLM. Is there any question for that? Yeah.
So our goal is just to generate representations. The outputs are just representations.
For the encoder?
No, for like encoder-only LLMs.
For the encoder-only LLM, it can.
And then would you have like a final layer
which can output tokens, yes. Yeah. But by itself, it just outputs hidden states.
And for decoder-only LLMs, like what is the difference? Would their functionality be?
The decoder-only LLM already has that component of outputting tokens, but it definitely also has the hidden state.
Okay.
Cool. So, so that is basically the recipe for our encoder-only and decoder-only LLMs. And as you might have guessed it, there are two LLMs, flagship LLMs that we're going to discuss today. So that's basically the encoder-only LLM, that's called BERT, and the decoder-only LLM, that's called GPT. Both are pretty famous. I'm sure some of you have already heard about it now. So let's talk about BERT first. It is called bidirectional encoder representations. This name is pretty canonical. You know, you can basically everywhere tells the story. So the motivation behind this sort of big LLMs, because the reason why we talk about BERT and GPT is because they're sort of the first LLMs that's ever been, right? So the motivation has been that the big challenge in model building used to be the lack of task-specific data, because when you train an LLM, chances are you're going to want it to perform on some task, right? And whatever task it is, you're going to have to manually label some data. And that basically means there's very, very few amounts of data, and you can't train a large model effectively with small amounts of data. So the idea is, what if you train an effective representation that can be applied to a variety of downstream tasks, and we can train that sort of representation with unlabeled data or with sort of large scales of data that it can sort of just self-supervise to learn. And that is kind of the motivation with BERT, specifically in 2018. I think yeah, the title here says 2018. So there has been some efforts in that respect into training a representation of text tokens and sort of see how it performs on downstream tasks. We have Word2Vec, we have Glove, that's like sort of precursors to the BERT approach, but those are made relatively earlier without the assistance of transformers, so that is not nearly as powerful as what BERT has been. So here it should be real clear that BERT is just the encoder side of the transformer, right? BERT does not have an explicit decoder. All right, so BERT is pre-trained on this sort of corpus. Again, not really large by today's standards, but is considered large in 2018.
Oh, can you clip your mic outside of it?
Let's see.
We got a feedback from just like keep your head out.
This might be better. Okay. All right, sorry about that. BERT is pre-trained on the two tasks that we're going to discuss today, which is masked language modeling and next sentence prediction. And just so you know, after these two tasks on these corpuses, BERT is trained to be this large. Again, 110 million, 340 million is not really large by today's standards, but that's considered one of the largest at that time. So, okay, let's go into detail what is meant by MLM and NSP, right? So if you think about how BERT reads in text, down here in blue is sort of the text that we take in as inputs, and they go into BERT, and BERT outputs still these tokens, but a enhanced representation of each of these tokens, right? So with masked language modeling, we basically fetch a corpus from the internet, basically from those two corpuses that we just described. And we randomly mask 15%. It just happens to be 15% in the entire BERT paper, but it can be any ratio. We mask 15% of tokens in that space. And let's say we mask this token, right? How are, this is a mask right here. And it appends tokens in here in this format, and BERT, after reading this sequence, outputs a sequence that is as long as this, which means that there's a one-to-one mapping between BERT's output and the original input in terms of each token is still its own, but it now is an aggregate information representation with taking information from other tokens, right? And sort of when you take in the mask representation at the end of the BERT output, then you can append a prediction head onto that neuron, onto that representation for that token, and you will basically be able to decode it into token space. And when you decode into token space, that can be interpreted as generating a token, right? And if you do a softmax there, then that will basically give you the probability of BERT thinking the probability of each token occurring at that place. So basically, you can see these numbers are made up, by the way, but you get the idea of how you can use BERT to mask a token and then get an output, and that output will tell you how probable each token it is to occur there. So this is basically mass language modeling, and we take the loss again with the usual deep learning. We take the loss between this distribution and the real token, which is just a one hot vector. We take the loss between that, and we use that backpropagate and update all the parameters in BERT, which is the same old story, right? So this is, I think that's mistyped there. That's a typo. This is actually NSP. This is next sentence prediction. So the way to do that, the objective there is not for BERT to predict a masked token. It is for BERT to predict whether one sentence is an immediate neighbor of another. So basically, you append these two sentences together, you concatenate them together, and delimitate them by this classification and separator tokens. And again, you feed it through BERT, and BERT gives you the aggregate representation of each of these tokens. And you just append the same prediction head to the classification token, and now that will only map it to 2 dimensions, so dimension 2. So that basically gives you just 2 choices. And when you have the logics, you take the softmax, it gives you the probability, and it will basically, you can interpret that as whether one sentence is the next sentence directly following another, or whether they are totally unrelated, right? So the idea here is that the 2 pre-training tasks in BERT, they teach BERT how to infer tokens from tokens, and how to infer sentences from sentences. So basically, that's token level pre-training and sentence level pre-training, right? And the end result is that the prediction head is highly task specific, right? The prediction head is not useful if you are not interested in predicting sentence neighboring, or if you're not interested in predicting a mask. But the rest of the BERT parameters are highly useful in that they are highly versatile in other NLP applications. And it turns out that when the model is trained this way, only the encoder, by the way, when the model is trained this way, it can be applied to downstream tasks pretty easily. And the way to do that, the way to apply BERT to any downstream NLP task is to apply a head that transforms the last level representation to the desired dimension that you want. And that is all you need to do to apply BERT to any task. For example, you want to have a classification task. Let's say you read in a sequence and classify something, right? Maybe it's token representation. If it's token representation, you need to have a decision for each token, right? So you append the prediction head for each token there. And then now you have let's say you have 7 classes available. So you map the hidden representation to a dimensionality of 7. Now you have a prediction. If you want to do sentence level prediction, you just apply the prediction head to the classification token. Now you have a aggregate representation for the entire sentence. So basically, the takeaway is that the prediction head is highly task specific. You probably don't want to use that from pre-training. You probably will have to train that from scratch, but that is a very, very small amount of parameters compared to the rest of BERT. And the rest of BERT is highly versatile and transferable into any sort of, English at least, English natural language text that you want to perform. All right, so just to get some context, BERT is evaluated in the GLUE evaluation dataset and also SQuAD question answering. And here are the results. You do not need to look at these numbers specifically in this lecture. The slides are up there, you can download. But the short takeaway is that BERT is competitive against the state-of-the-art models in 2018. So basically, you can see the bold text in this bottom row in this table. That means it is comparatively the best model, and BERT large is the best against all the other models that it could find in 2018. So the end result, the takeaway here is that through this kind of pre-training, BERT has been really competitive. All right. So this is kind of an interesting phenomenon because if we think about it, it doesn't really make sense intuitively to try to mask out something and predict it. How is it even useful? If you want to have an NLP model, chances are your task is not going to be predicting a mask. You probably want to do something useful, such as classification or question answering. It does not necessarily mean you want to do predicting a mask. However, the creative invention of this MLM task and the NSP task, how could you even come up with it? But when you come up with it, you train a model that way, it happens to be transferable. And that is pretty creative. And so the first takeaway from BERT we can learn is that if we train an effective representation, that means we need to have flexible regime of pre-training tasks. And that basically means that the creativity in coming up with this pre-training task is vital in making use of large amounts of unlabeled data, because how else are we going to self-supervise the model? To learn from that data, we have to have some creativity in the pre-training task, and that's what BERT has done. The second takeaway, we also learned that different NLP tasks seem to be transferable with each other, and that's something that we were not used to in 2018. So basically, the takeaway is that as long as we have effective representations, that seems to give us a generalist model that can perform any task, right? It can perform question answer, it can perform anything as long as it has effective representation. So the transferability seems to mean that within the class of NLP tasks, at least, within that class, tasks itself are highly transferable. I mean, the weights that you get from training on the MLM and NSP happens to be useful for question answering. I mean, it's not even trained on question answering. It's just trained on that task that you're not going to use it for, but somehow that weight is useful. Yes, do you have a question? Cool. So the third takeaway is that scaling works. I mean, in machine learning, we always thought that when we grow the number of parameters in a model, there is going to be a growth in the power of the model as well. And BERT is sort of the first large language model to prove that. Basically, 340 million, which is the size of BERT large, is not really large, but it has proven that with the growth of the model, I mean, provided you have enough data to train it, then the model is actually going to perform really competitively. So that's BERT. Yes?
For the training tasks, did the masked word guessing have to be pre-trained before doing the sentence guessing? Like, did you have to have some understanding of what word embeddings look like to then do sentences, or were those kind of independent?
So that detail I don't have on top of my head, but my reasonable guess is that it should know the tokens before it knows the sentences. Otherwise, it does not have a deep understanding of the tokens, so it cannot understand the sentence. But that's my reasoned guess here. All right. So let's take a look back at this. So we just explained how an encoder-only model can be made to be an effective language model, right? It only outputs hidden states, but that hidden state you can use to map anywhere. So really, that is a general purpose language model, right? And now let's look at what it means for a decoder-only model to be a language model. Yes, question.
Question. So you said that you are reusing this encoder that you train on encoder task. Like when you are training this new head, are you training the whole network at the same time, or are you kind of freezing the weights and just using this encoder as the input to this new prediction head?
So there are two questions here. So really, there are two cases here. One is during the pre-training, and one is during the actual fine-tuning. So the short answer is yes, you do update the entire model, including the prediction head. And the reason is that during pre-training, you definitely want to update BERT itself. You don't want to update the prediction head because you're going to ditch the head eventually when you apply BERT to something else, right? The prediction head is task-specific in that if you just update that, then that's not going to be useful if you want to have a model in itself, right? Because that's actually not part of the model that you release in BERT. And when you do the actual fine-tuning, I guess you can freeze the weight of BERT itself, but then I think the general practice has been that you update the whole thing just because it's not so large. It's convenient to do that. But with larger and larger models, especially nowadays, then it's probably more popular to freeze parts of the model and just train parts of it. All right, so let's quickly talk about what it means to have a decoder-only model. So GPT is called Generative Pre-trained Transformer. It's probably a useful knowledge to know, considering how popular these three letters have become, and it's kind of weird if you don't know what it actually stands for. It is similarly motivated as BERT in that people realize that there are large amounts of unused data lying around, and it's best to make some use of that without the need for human labeling for your specific task, right? And GPT is trained on this corpus, I think really similar to BERT. And the pre-training task is not that kind of MLM or NSP as BERT. It is just trained on the very simple task to predict the next token given the previous tokens in the corpus. So let's say your corpus is, I ate an apple today. So from I, you need to predict 8. From I ate, you need to predict N. From I ate N, you need to predict apple. So that's the same kind of prediction, the step-by-step decoding that we just saw earlier in this lecture. And the pre-trained results is a GPT is kind of this big. Again, not really big, but kind of big when it came out. So we have a model that is capable of reading some text. Basically, that text is either it produced that text itself or that text came from the training, right? And it's capable of outputting text. So how do we use it to some downstream task? We just demonstrated how to use BERT to a downstream task. You apply, you append a prediction head, you append whatever head to BERT, and that's how you use BERT for any task. How do we use GPT for any task? So GPT is unique in that it's actually trained on generation. So you can actually let it generate, and that's how you use it to perform on tasks. So basically, you can format your task-specific text as a continuous stream, and you use the model to predict that stream. So that is a convenient way you can use GPT to perform any task compared to BERT, because BERT, you have to train some parameters. With GPT, chances are you can just prompt it. And by prompting, I mean, if you really wanted to summarize an article, then you just give the article and you append it to the prompt, summarize this article, and just say, the summary is, colon. And if GPT really understands the language, then GPT will continue on to give you the summary after this colon, because that's the most reasonable continuation of that text stream, right? And similarly, you can format any task in this way. So to have GPT just sort of continue the text, and that's how you will perform. And as I said, GPT is not only capable of this. I mean, of course, it has hidden states. So if you just do not use the output layer and you look at the hidden states, then you have basically BERT. I mean, it's trained differently. It is used to only seeing text before and not after, unlike BERT. So it's kind of different in how you would actually use it. But theoretically, you have the same sort of capability in that you can also use the hidden state, like how you use BERT hidden states. But you also have the ability to use the tokens generation ability directly in this way. That is how you apply GPT to sort of downstream tasks. All right. So I will not include the GPT evaluation because it has been included in the BERT evaluation here. And the reason for that is that BERT came out a little bit after GPT, so BERT creators had the power to sort of beat GPT in their paper. And we always think the BERT is kind of the flagship LM more than we think about GPT, but I mean, maybe that is an artifact of when they came out. But it is interesting to talk about both of them because it is sort of a comparison of the different paradigms of how we train an LM that is used to outputting hidden states versus an LM that is used to outputting tokens. And both of these are really useful in various downstream applications. We just demonstrated how you can use both for any task, but it is important to know that if something is pre-trained on generating, then it's probably best to use it for generating, versus something is pre-trained for representation, which means outputting hidden states, then it's probably best to use that hidden state in some way. So classification, probably BERT. Generation, like summarization, because summarization, you need to output actual human readable text, right? Summarization, probably GTP. All right, so what do we learn from GPT? Again, these are pretty similar stories as what we learned from BERT. The effectiveness of how we can use a model and let it just self-supervise, which basically means not supervising, just let it self-form some sort of guidelines, some sort of loss, and some sort of text task that it can take with itself on a large amount of unlabeled text. That is more powerful than taking the model and fitting it on some task on specific task-specific data that we might cook up. It turns out that the vast amount of data is more powerful than well-made data with a small amount, right? It turns out that GPT is a knowledge base. And by that, I just mean transferability. It's just the same point as what I said in BERT. You have a generally pre-trained models, and that have a decent zero-shot performance on a range of NLP tasks. I mean, that is pretty similar. I mean, this sort of zero-shot performance thing is kind of ordinary today, but back in the day, you would think that when you want an LM to perform on some task, you would need to train it on that task, right? That's sort of, when you take introduction machine learning, that's sort of the paradigm, right? You want a model to perform on this, you got to train it on this. If you train it on something else, chances are it will not perform on this. But GPT just demonstrated that with large amounts of unlabeled text, you can actually have zero-shot performance on some tasks, which is pretty interesting. And again, scaling works. You have sort of a large kind of model, and given enough data, you can always train that model to be performance. All right, is there any question about GPT? Because there's a quiz question right after. Yes?
If there's no encoder, then what does the key end value in the second block of the decoder?
Very good question. So if you look at this, where's my sword? You're wondering what comes in from this arrow, right? So basically, if you think about what should come in this arrow in a complete transformer, encoder hidden states should come in, right? And what do they even carry? Encoder hidden states carry representation on text that came before whatever you want to generate, right? And with GPT, what kind of component carries that information, which is basically what kind of component tells you about the text that came before? It's just the hidden states that came before, right? It's just the hidden states in the GPT model that they also read in information before the kind of text we want to generate. So really, this cross-attention is the same as self-attention if we really interpret GPT as sort of the encoder that reads in output text. Because think about it, the input text that we would usually feed an encoder, we are feeding GPT in this case. So really, GPT is both our encoder and decoder. It's just we do not explicitly use another encoder. So really, you don't need this arrow. We just directly use the multi-head attention within itself, and that will serve as cross-attention because it is attending to the tokens that came before it. Yes?
So the only real difference between an encoder and a decoder when you separate it out is the masking of previous tokens in a sense?
Exactly. So the difference between them are the 2 points that are a couple slides before. I'm not going to scroll back. But basically, the only difference is that the decoder can only see time steps before, where an encoder can see all the time steps. And that decoder is autoregressive and it takes in its own output, whereas an encoder only takes in text. But those things can be fixed. So that when you fix these two things, that I listed left, right, on the previous slide, if you fix those two things, then they're exactly the same. And if you look at the diagram, multi-head attention, add norm, feed forward, add norm, exactly the same. Okay, the only difference is this multi-head attention. And if we think about using a decoder to read in text, then its representations, its hidden states are sort of the same as what we would think about as encoder hidden states. So really, they're the same. Yes, last question, yes.
Good question. Like hypothetically speaking, isn't it possible if we create a new model that will include BERT and GPT, so we'll use BERT as encoder and GPT as decoder?
Yes, you're thinking about a complete sort of transformer with an explicit encoder and another explicit decoder, yes, and we'll talk about that in a second, very briefly, but yes, that is possible. So basically, yeah, you just feed hidden states to a decoder and you job with that, yes, that is possible. All right, so I believe here's a quiz for you. We're gonna give you 1 minute, sort of short on time.
1 second. Yeah.
All right, yeah, not really hard. Uh, 8 seconds. All right, what do people get? Million, exactly. You need to know at least what these numbers look like. All right, so these two models really open up a sort of what we call an LLM era, in that they are sort of the first LLMs. If you think about when did LLMs came about, you probably think about, from a everyday point of view, you might think ChatGPT that came out last year. But really, the sort of the LLM paradigm came out with these two models. And I'm going to explain in more detail why I think that is. So after BERT and GPT, obviously, if you read some of the ongoing discussions, there are sort of children on their own, Dilbert, Roberta, Albert, Electra, Deberta. There's sort of a naming convention there. And with GPT, 1, 2, 3, 4, 5, there are a lot of GPTs. And with sort of in the middle, these are sort of models with both an encoder and a decoder, so explicitly. So Katya, that is T5 part, multilingual T5. These are mainly for translation, because that's what the original transformer architecture is designed for. It is designed for translation. It's just the BERT creators and the GPT creators got smart and used parts of it for other things, which is totally unintended. I mean, maybe not totally, but it is unintended, at least from the original paper that introduced the transformer, in that transformer is just for attention originally. But now you have all these models. And what seems to have happened with these models is that they provided a new class of what we call generalist models that are able to capture things that are more fundamental than specific tasks, right? And this really has caused something bigger than what it might seem here. So let's compare from a researcher point of view the kind of questions that researchers like us at the university or even in companies think about before the LLMs came about and since they came about, right? So before they came about, what did machine learning practitioners think about? They think about the feature engineering. I'm sure that quite a few of you might have predicted housing prices in California. And what kind of features do we use for that? You might think about, oh, maybe we use the house, the kind of the area, the number of bedrooms, the kind of location, right? These kind of features are vital for tasks. So what kind of features do we specifically, explicitly select for tasks like that, right? Model selection, which model is best for which kind of task? If you have a classification task, do you use SVM, do you use decision tree, do you use whatever, right? Different models are suited for different types of tasks. Transfer learning, for any task, the amount of data is definitely scarce. So how do you use other tasks to train a model to perform your task, right? And overfitting, when training a model, how do we balance complexity and capacity to make sure that our model performs decently, yet still does not overfit catastrophically? So if you think about, if you look at these things on the left yet, not even on the right, on the left, how much of that do we even do from a machine learning or even like specifically NLP researcher point of view? We don't select features that much, right? Our feature in the NLP domain, our feature is just text, right? And sort of they're everywhere. And the more we have, the better. Right? It's not like we can have too much data to start with. Model selection. What kind of model? I mean, there is a sort of comparison between encoders and decoders, but sort of every model is now some sort of a transformer, right? You don't think about using other models for any type of task now, at least in the NLP domain. Transfer learning, yes, I think we still do some of that, right? But the motivation of doing transfer learning now has been different. It's not because it's not so much anymore because task-specific data are scarce. It's probably because that we have such an abundant body of unrelated data that we probably want to make some use of that, right? Overfitting, I don't think LLMs overfit quite easily anymore, right? We have so much data. Overfitting happens when you have too small body of data, right? Now you have so much data, LLMs don't easily overfit anymore. So really, these things, we don't concern ourselves as often since LLMs came about. So what kind of questions do researchers think about today? Pre-training and fine-tuning. How do we leverage large amounts of data that is previously unused, right? Zero-shot learning. How do we even make models perform on tasks they're not even trained on? Again, this is sort of the thing that only LLMs provided us. Before LLMs, it's not imaginable. I mean, if you don't train it on some task, you're not going to have it perform on that task. But now with LLMs, it's possible. How do we even make models understand their tasks simply by prompting it? That's sort of the example that I gave with GPT. So sort of you embed a summarization task with sort of summarize this article and question answers and end task that way. And interpretability and explainability. So basically, we don't seem to understand our models anymore. When a model outputs a certain token, why does it do that? Right? Before, machine learning had been such a theoretical science in that you write out the equation, you write out the gradient, and you calculate everything on paper, and you prove that your theory works on your machine. Right? The theory comes first, and the experiment comes later. That's sort of the paradigm of LLM, or with machine learning before LLMs. And right now, what you do is sort of, you design an experiment. You don't even know what's going to happen. And now, you do an experiment, and you invent theories to explain what you get in your experiment. So sort of, experiment comes first, and theory comes later. Right? So really, this is the kind of paradigm shift I want to highlight here that is introduced by LLMs. All right, so yeah. What has caused this paradigm shift? If we take a look back at how we got here, then sort of the problem of recurrent networks, which is what got us in the discussion into attentions in the first place, is that, remember, in recurrent networks, information is lost during the encoding of a long sequence, right? If you think about it, if you encode a long sequence, then sort of all the information in there is encoded in the last hidden state, in the last time step. And that introduces a bias towards later time steps as opposed to earlier, right? So we really wanna fix that problem, and the sequential nature of that kind of network disables parallel training, and you can't scale that model really easily. So we invented attention, right? Attention is good at handling long-term dependencies, in that you can have any time step attend to any other time step so that you don't have to sequentially process a model. So it really solves the kind of information loss problem in the first line here. But it also just so happens that it has solved the parallel training problem, because when you don't have to train something sequentially, then you can train that parallelizably. And with that, you can basically scale up the model with relatively little time cost, right? And I don't know whether that's intended with the original introduction of the attention, but really that has allowed us to scale up our model drastically. Before attention, there's very small models, but after attention, there are very large models. And parallelizable training is definitely the core of that. So if you think about it, attention and transformers are really the core to the big models that have given us these emergent abilities that only came about with large enough models that has introduced that, that sort of paradigm shift in the kind of questions that concern us the most. All right, there used to be a quiz here. I'm not going to do it, but I was going to have you think about what might be a flaw of our current transformer-based LLMs. We're going to publish the note after this lecture. You might just do follow-up discussions. And if you want, this is something that you can think of, probably not for the project this semester, but independent studies or whatever. Come talk to us. This is a pretty interesting topic. Just like LSTMs are bad for sequential output, we had to invent attention. What kind of innovation might there be in our current transformation, in our transformer? Right? This might not be the end. Transformer and attention. These are certain things that I have typed up. This is my example. It's not guaranteed to be correct, but there might be further algorithmic architectural innovations needed for transformers of today, right? And that's something you need to think about. And for the last slide, I want to highlight that at the core of the transformers or machine learning models in general today are a lot of powerful components that, when we think about it, the core of predicting performance in these models is predicting the next token, right? And predicting the next token is the same as drawing a sample from a distribution. And the reason why that might be very powerful, and we observe that power of that simple mechanism, is that any problem in the world can be formatted as drawing a sample from a distribution. And drawing a sample from a distribution can be expressed by predicting the next token, right? So really, I'd like to close today's lecture by quoting Sam Altman. Language models just predict the next tokens, but that's not as simple as you might think, because humans, including us, are just animals, are just programmed to survive and reproduce. And yes, here we are today. So really, there are hidden powers in certain components that are more fundamental than you think. All right, that's all we have for today.